This is section 10.3, Parametric Equations and Calculus. Okay, so this too is a review section from your pre-calculus course, and then we'll be getting right into the calculus aspects of this. So in the last section we talked about a projectile that we use these parametric equations to describe its motion in the xy plane at various times t. Okay, and so these of course give us a position of the projectile at any time that we want. Now we know that the object is initially projected at an angle of 45 degrees. So the slope, of course, which is change in y over change in x, is the tangent of the initial angle. And of course that's 1. Just as a review, the tangent of an angle is defined as y over x if we have an angle in standard position, and this is y, and this is x, opposite over adjacent. So if you're given the angle at which it's moving to the horizontal, then the tangent of that angle will give you the slope. And that's just the initial slope. And then of course as the projectile moves, so at this point right here, the slope of the tangent line is 1 because we're at a 45 degree angle right there. But at a later point in time, let's say right here, the tangent line slope is going to take on a different value, and that will depend on the angle made with the horizontal of the tangent line at that point. And so to find the slope at some other time t, we're going to have to find the slope by using, because we won't be able to find that angle necessarily. What we're going to have to do instead is find, like we did in Calculus 1, the slope is going to be found using the first derivative of the function. Now, of course, that's in terms of y and x, as dy dx, and our functions are in terms of t. So in order to make that happen, we're going to have to think about what we can do with what we have. And since, for example, y is a function of t, I could find dy dt, and by the same token, x is a function of t, and I could find its derivative, dx dt. And notice that this simplifies, this ratio of dy dt over dx dt would simplify to be dy dx because the dt's would cancel out. If you think about multiplying the numerator by the reciprocal of the denominator, you'll see that the dt's would cancel. And so this is the formula for finding dy dx parametrically, is that you find dy dt and you find dx dt separately, and you form that ratio. And of course you can't divide by 0. Okay, so let's take this example up here and let's find dx dt. So I'm looking up there at the top, and down here I'm doing its derivative. And of course, the derivative of a constant times our variable is the constant. Remember, we're differentiating with respect to t. And then dy dt is negative 32 times t plus 24 square roots of 2. And so the implication, therefore, is that dy dx will be dy dt, which we just found to be negative 32t, plus 24 square roots of t, divided by dx dt, which is 24 square roots of 2. And so if we multiply this to rationalize the denominator, we'll multiply it by square root of 2 over square root of 2, that form of 1. And we'll get negative 32 square roots of 2 times t, plus 24 times 2 is 48, divided by 24 times 2, which is 48. And there's a common factor of 16, so I'll divide that out of everywhere, leaving negative 2 square roots of 2 times t, plus 3, divided by 3. And so if you give me a time, like half a second, 1/2 for t, you could find the slope of the tangent line at that point in terms of t. So notice that you have to know t to find the slope of the tangent line at that point, because this derivative is in terms of t. Again, it's a parametric form of the derivative. So let's do another example of that. Let's say that we have x equals sine of t and y equals cosine of t. By the way, my preference here is for you to separately find dx dt and dy dt, and the reason for that will become clear pretty soon. So I don't want you to go straight to the derivative of this thing over the derivative of that thing. I would really prefer that you write this derivative down first and then form the ratio. And again, I do have a reason for that. It's not just arbitrarily chosen. So we find the derivative separately of dx dt and dy dt, or I'm sorry, find the derivative of x and y separately. Then dy dx is the quotient of those two. It is dy dt, which is negative sine of t, divided by dx dt, which is cosine of t. And then simplifying that, we get the opposite of tangent of t. Okay. Now, if we wanted to know something about concavity, we would need the second derivative. And I'm going to use Leibniz notation because to me it makes a whole lot of sense with how this formula is going to work. So the second derivative of y with respect to x and then with respect to x again, that's going to be found by taking, as we did in Calculus 1, the derivative with respect to x of our first derivative, dy dx. Okay, well, so far this isn't anything new, but keeping in mind that we're doing this parametrically, to do that, we're going to have to take the derivative with respect to t of dy dx and that part you probably would have thought of doing, take your last answer and find its derivative. But if you look at the notation there, that's d squared y, but dt times dx, which is not dx squared. So that's not quite what we want. And to make it work out, we want to get rid of the dx and introduce another dt. I'm sorry, I said that backwards. I want to get rid of the dt and introduce another dx. So to do that, I can do division by dx dt. So if you think about multiplying the numerator by the reciprocal, you'll have 2 dx's in the denominator, and you'll have dt in the numerator to cancel the dt that's in the numerator right now. And so the denominator of the numerator, I should say. So that's how you do it. And this is why you would need to do these separately, because you're going to need that dx dt again. So it's not as simple as Calculus 1 where you just take the derivative of your first derivative to get the second derivative. You then have to divide by dx dt. And that's going to be kind of a way that we proceed for all higher order derivatives. If we want the third derivative, we'll take the derivative with respect to x of our second derivative answer, which was with respect to x twice. And just like we did in Calculus 1, we're going to take the derivative of our second derivative. But since it's in terms of t, we have to take the derivative with respect to t. So that'll be the derivative of our last answer. But again, the differentials don't work out, so I'll have to divide by dx dt to cancel that dt and introduce another dx. And so again, it's the process will be take the derivative like you would normally, but then you'll have to remember, then divide that answer by dx dt again. And that's going to be one of the hardest things to remember, I believe. So let's go back to our example that we did earlier. It's right up here, this one. And let's find its second derivative. So I'm just going to do this over here. So we're going to take the derivative of our answer, and that will give us negative 2 square roots of 2 over 3, because that's the constant in front of t. So the derivative of the constant times t is the constant, plus 1, and the derivative of 1 is 0. So I didn't write that. So this is the derivative of our first derivative answer that we see above, and then we're going to divide that by dx dt, which, if you'll recall, was 24 square roots of 2. Okay, then rationalizing the denominator, we'll multiply by square root of 2 over square root of 2. And also, to clear the equation of, well, I'll do it in 2 steps. Let's take care of the radical first. And so negative 2 square root of 2 times square root of 2 is going to be negative 2 times 2, which is negative 4, over 3. And that'll be 24 times 2, which is 48. And then you can think of clearing the fraction of fractions. You can think of that as multiplication by 3 over 3 if you prefer. Or you could just say division of negative 4/3 by 48 is negative 4/3 times 1/48. However you approach it, you should get negative 1/36. And now let's find the third derivative of that same, oops, I wrote a 2. The third derivative of that same set of parametric equations. So it's going to be the derivative of our last answer, the derivative of that constant is 0, divided by dx dt, 24 square roots of 2, which is just simply 0. All right. So now the next thing I'd like to look at is the arc length formula for parametric form. So in theorem 10.8, we'll have smooth curve C given parametrically, and C will not intersect itself on the interval from A to B, except for possibly at the endpoints, then the arc length of the curve will be the integral from A to B of the square root of dx dt quantity squared plus dy dt quantity squared dt. Okay, so I'd like for you to see how that's developed. So let me spend a bit of time with that. So let's start with the formula that we had before for a function y in terms of x. This is the formula we had. And if I were to take this formula and try to create a formula in terms of t, I would need to introduce some things to turn this into a integral in terms of t. So the first thing I would introduce would be something to get rid of that dx. So I need a dx in let me see what I want to do. Well, I need to introduce let me think. This was so clear in my head just a second ago. Oh yes, that's it. I'm going to multiply by this form of 1, dt over dt. Then I'm going to change this into the same thing as what I have above, but in a different form. I'm going to make this dx dt, so I pull that dt in the denominator over, times dt. Right. Then I can rewrite the dx dt as a radical and that's the same thing as saying the square root of dx dt quantity squared. Then if I distribute that into the other radical, since they're under the same radical, you can just multiply the radicands together. 1 times dx dt squared is dx dt squared. And dy dx squared times dx dt squared, the dx squared in the denominator of the first part of that times the dx squared from the numerator of the second part will cancel each other out, leaving dy dt quantity squared dt, which is the formula that I gave you above. All right. Then the next one I'm going to give you, I believe, without developing this idea from scratch like we did this one after the fact. I'm just going to give you this. So the surface area of a solid of revolution is very much like what we did before. We would take this formula and multiply it by the circumference, which is 2 pi times the radius. So the surface area formula is going to be 2 pi times the integral from A to B multiplied by the radius. So the radius will be some function of t times the same radical expression we have from the arc length formula over to the left. dt. And that radius is going to be the same radius that we had before. Like if we had a region like this being revolved about the, say, the x-axis, then the radius is the distance from the axis of revolution to the curve, which is y. And since it has to be a function of t, we would use the g of t in that position as a representative of y. On the other hand, if, for example, we revolved something about, let's say this is, relabel this up here, this was g of t, is the y. Well, it's actually both. It's parametrically defined. So it's x equals f of t, y equals g of t. Okay, so if this one over here had the same kind of definition, but instead of revolving around the x-axis, we revolve about the y-axis, the radius will be the distance from the axis of revolution to the curve, which is x, which would be, in terms of t, f of t. And so you can see how that radius function up there of t, if revolving about the x or y-axis, is simply f of t or g of t, depending on which one you're revolving about. Again, this is one of those times where I would draw a good picture so I can understand what's going on and then figure out what that radius function will be for that particular problem and go from there. All right. So let's look at example 2. Part A, where we're told to find an integral expression for the area of the surface of revolution when a curve that is defined as x equals 1/4 t squared and y is equal to t plus 3 for the interval from 0 to 3. And if that's revolved about the x-axis. Okay, so you might want to have a picture of what this looks like. It's not really necessary, so let me just say that it might look something like this. It doesn't, this is probably not perfect, but it doesn't really matter. Let's say it looks like that because I really don't know. And we're revolving about the x-axis. And so that means that our radius is y. And that's what it is in terms of t plus 3. So the surface area is 2 pi, using the formula that I wrote up above, times the integral from 0 to 3 of our radius function. Notice because it's a binomial, it has to be written inside parentheses to protect its nature, times the square root of Now this is what I forgot to do. Usually I do this right away, and I just neglected to because I got busy with the picture. But usually the first thing I'm going to do is find dx dt, which is 1/2 t, and dy dt, which is 1. So that'll be dx dt 1/2 of t squared plus dy dt 1 squared dt. Okay. And we can leave it just like that because they ask us for an integral expression, and that's it. If you can't stand it and you feel like you've got to simplify something because you just don't like the way it looks, don't go too far, because if I just ask for the integral expression and you have it right and then go too far and mess up something, you're going to lose some points. So please be aware of that before you do any simplification, because I would take this answer. Anyway, this would simplify to be 1/4 t squared plus 1 dt. If you just can't stand it, you have to do a little simplifying. That's it. Okay, but I would have taken the first answer I wrote, unsimplified, because if they just want an integral expression, I'm not looking for the simplified expression necessarily. Okay, let's go to part B. Find the slope and concavity at t equals 2 for the curve defined parametrically as x equals the square root of t, aka t to the 1/2, and y is the square root of t minus 1, also known as t minus 1 to the 1/2. So because we're doing slope, we're going to need dy dx, and that's going to require that we find dx dt and dy dt. And then the slope at any time t will be the dy dt answer divided by the dx dt answer. Okay, you might notice that the 1/2s will cancel each other out, and we can get rid of the negative exponents by taking that power to the other part of the fraction. So this would become t to the positive 1/2 over t minus 1 to the positive 1/2. And if you care to, you can make that all under one big radical, the square root of t over t minus 1 if you prefer. What we're asked to find in this problem was the slope when t is 2. That's why we found the first derivative. The slope, therefore, is our derivative, dy dx, evaluated when t is 2. So by substitution, that's going to be the square root of 2 over 2 minus 1. So the slope is square root of 2. And of course, what we could imply from that is that because that slope is positive, the graph of that parametrically defined function is increasing at time t equals 2, something we could infer from what we've done. Okay, then the other part of the problem is for concavity of this curve, which concavity comes from the second derivative. So we need to take the derivative of our first derivative answer. And so let me see, how do I want to do that? Yeah, okay. I'm going to look at this version right here for doing the derivative, because we really don't like radicals when we're doing derivatives. So I'm going to look at that, and that's a quotient. So I'm going to have to use the quotient rule. So that's going to be low times d high, low d high, minus high d low all over the square of low. And again, I realize that a lot of you can do this squaring in your head and go straight to an answer, and that's great. I'm writing all of these steps for clarity. So that when you come back and look at this later, you know exactly what's been done to get that. Okay, so that's the derivative of our first derivative answer. But then don't forget, this is the easiest thing to forget because you've done a lot of work up until then, that has to be divided by dx dt. So divide that by 1/2 t to the negative 1/2. Okay, so that division by 1/2 t to the negative 1/2 is the same thing as multiplying by its reciprocal, and its reciprocal would be 2 t to the positive 1/2, okay, times that answer over there of that, what that is. So let's simplify that a little bit. Let me see, I'm thinking just a second. I want to make sure I know what I'm doing here. Okay, so what I want to do is I want to factor that numerator that I've written in pink and look for common factors. So 1/2 is a common factor in the numerator. Some power of t is a common factor. And remember, when you have common factors, like if you had x squared minus x to the 7th, the common factor is the greater or smaller power of x. It's the smaller power, right? And you get what's left by division. X squared divided by x squared is 1, minus x to the 7th divided by x squared is x to the 5th. So kind of keep that in mind, because that's how you do this process. So for the powers of t, is negative 1/2 or positive 1/2 smaller? Well, obviously the negative number is smaller than the positive number. So t to the negative 1/2 is our common factor. And then there's a power of t minus 1 that's a common factor. Same song, second verse. The common factor will be the lower power to the negative 1/2. So if I divide the first part of the numerator by 1/2 and t to the negative 1/2, that leaves 1 times 1 inside. And then here's the kicker, t minus 1 to the 1/2 divided by t minus 1 to the negative 1/2. Remember, to divide, you subtract exponents. So it'll be t minus 1 to the 1/2 minus negative 1/2 is 1. Minus, then if you factor out the 1/2 and the t minus 1 to the negative 1/2, they're going to leave ones, invisible ones. And then we're going to divide t to the 1/2 by t to the negative 1/2 and get t to the first. And in the denominator of that, t minus 1 to the 1/2 squared, of course, is just t minus 1. All right. So if you multiply 2 times 1/2, you'll get 1. If you multiply t to the 1/2 by t to the negative 1/2, you'll get 1 because you add the exponents. So it'll be t to the 0, which is 1. The t minus 1 to the negative 1/2, if I carry that down to the denominator and combine it with the t minus 1 to the 1 that's already there, 1 plus the half coming down as a positive, exponent, we'll make that t minus 1 to the 3/2. And then we're left with whatever this simplifies to be. And that'll be t minus t, which is 0, minus 1 is -1. And so there's our second derivative. So the concavity is found at a particular time by evaluating our second derivative at that particular time, time 2. That's going to be -1 over 2 minus 1 to the 3/2, which is -1. And the concavity is, the answer to that is it's concave up or it's concave down. And so you look at the answer we just got, and because that's a negative number, that means that the curve is concave which way? When the second derivative is negative, the curve is concave downward. At time t equals 2. Okay, and so there you have that one. All right, so let's move along to example C. Find all points, if any, of horizontal and vertical tangency to the curve x equals t squared minus t plus 2 and y equals t cubed minus 3t. Okay, so first of all, let's think about what horizontal and vertical tangency means. Let's start with horizontal tangency. You have a horizontal tangent line when the slope of the tangent line is what number? Now, when the slope, or dy dx, is equal to 0. And you have a vertical tangency situation, you have a vertical tangent when dy dx is undefined. And another way of saying that is when dx dy, its reciprocal, is 0, because 1 divided by 0, the reciprocal of dx dy would be dy dx, so the reciprocal of 0 would be undefined. And so that's what we're going to be looking for. So our big task is, what is dy dx, and then what are we going to do with it? So let's find dx dt. That's 2t minus 1. And let's find dy dt. That's 3t squared minus 3. And now find dy dx by forming the ratio 3t squared minus 3 divided by 2t minus 1. And that fraction is equal to 0. The only way it can equal 0 is if the numerator equals 0. So that would mean that 3t squared minus 3 would have to be 0. And of course the denominator can't be 0. 0 over 0 would be indeterminate. So if you look at that, that'll happen when t is 1/2, which won't be one of our answers here. So that's fine. If you factor out the 3, left with t squared minus 1. And then factoring that, you get t plus 1 times t minus 1. And that's when t equals -1 and t equals +1. Okay? Now, let's reread the question. It says find points. That means points on the curve. So what we're going to have to do is let t equal one of the values we found, -1, and we're going to have to calculate the x value and the y value when t is -1. So make sure you go back to the original declaration of what x and y are. X will be the input squared, t squared, minus that input plus 2. So that's 1 plus 1 plus 2 is 4. And then y of -1 will be input cubed minus 3 times the input. So -1 cubed is -1 minus 3 times -1, so that'll be plus 3. That's 2. So we have a horizontal tangent line at the point 4, 2. Okay, now let's let t equal the other possible value that we found, t1, t is equal to 1. So we need to find x and y when t is 1. So this will be 1 squared minus 1 plus 2, which is 2. And this will be 1 cubed minus 3 times 1, which is -2, which means we'll also have a horizontal tangent line at the point 2, -2. Okay, now for the vertical tangent lines. That'll be when dx dy equals 0. So that means that dx dy would be, by substitution, oops, I forgot to write dx dy. Will be 2t minus 1 divided by 3t squared minus 3. And that will equal 0 when its numerator equals 0, which we discovered earlier was 1/2. And the denominator can't be 0. And at 1/2, the denominator is not 0, so we're in good shape. So again, we're looking for the point when that happens. So we'll need to calculate what x is when t is 1/2 and what y is when t is 1/2. So this will be 1/2 squared minus 1/2 plus 2, which simplifies to be 7/4. And then y is 1/2 cubed minus 3 times 1/2, and that simplifies to be -11/8. And so that means we have a vertical tangent line to the curve at the point 7/4 -11/8. And what I'd like you to do is pick up your calculator and graph this parametric equation in parametric mode and look at the points 4, 2 and 2, -2 and make sure the curve has horizontal tangent lines there, and look at the point 7/4 -11/8 and see if the curve has a vertical tangent line at that point. And that should be very satisfying because it worked and it's correct. Okay, So that ends this this recording. I'm at the end of the page, so I will continue in the next part.